So what do we got going on tonight?
End behaviors,
Okay.
and they're all graphs.
Okay.
The first function is f of x equals x over x plus 4.
Like that?
Yeah.
Okay. And what do they want you to do here?
The vertical asymptote, the y-intercept, x-intercept.
All the standard stuff, okay. The best place to start, I have found, is with the vertical asymptotes. Where is the vertical asymptote in this function? Okay. About a horizontal asymptote?
Is that just 1?
Yeah. It's the ratio, if the degree of the highest degree polynomial is the same in the numerator as it is in the denominator, then the horizontal asymptote is the ratio of their coefficients, which in this case is 1 over 1. So there's our starting point, or rather there's our starting grid, and we know, let's see, let's go ahead and write x equals minus 4 is the vertical, and the horizontal asymptote is y equal 1. And let's see, they want all the intercepts?
Yeah.
Okay. What is the y-intercept?
Wouldn't it be just 0?
Well, what is true about x when we're on the y-intercept?
X equals 0.
So plug in x equals 0, what do we get?
0 over 4.
Which is 0. So the y-intercept is 0. So it goes through that point right there. Hold on a moment. There's something wrong with that. I'm not sure what it is. Well, let's figure out the x-intercept.
Wouldn't that be 0?
Also, in other words, I'm going to set f of x equal to 0, and the only way f of x can be equal to 0 if x is equal to 0. So our function goes through this point right here. Now, what does it look like? Wow. Typically, hyperbolic functions look like this relative to the asymptotes. Okay? But obviously, this one doesn't look like that. Ah, I see what's going on. No, I don't. Huh. Hold on. I got to think about this for a second. Let's see. If x was 2, then y would be down here. In other words, if I plug in 2 for x, y is 2 over 6, which is 1/3. So we must be in this quadrant down here. In other words, we must have a hyperbolic function that looks like that. And usually if it's in this quadrant here, then it's this quadrant up here also. In other words, that's what hyperbolas look like. Now, let's test this. If I pick a point minus 5, then I would have minus 5 over minus 1, which would be a positive 5, which would be up here somewhere. So we've got them in the right quadrants. In other words, we've graphed them correctly. It's interesting. I always kind of thought that in order to be in the second and the fourth quadrants, we needed a negative sign somewhere in there, but obviously we don't. What else did they want to know besides intercepts and asymptotes? There's no holes.
Yeah, That's it for this one.
Holes come from when you have a common factor that gets in the numerator and the denominator, and you can cross it out. You can't completely cross it out. In other words, if you have something like x plus 1 times x plus 2 over x plus 1, well, it looks like we would have a vertical asymptote at x equal minus 1, right? But that whole thing gets crossed out with that, leaving x plus 2 as the function, but not quite. There still is the condition that x cannot be equal to minus 1, and that's where the hole comes in. Not a vertical asymptote. Okay, what other function do you have?
X plus 3 over x, parentheses x plus 4.
X plus 3 over x plus 4?
Well, x, parentheses x plus 4.
Okay, I'm not quite hearing you well enough. What do I have at the bottom?
X, parentheses x plus 4.
Ah, like that?
Yeah.
Okay, so that's our function. Okay. Where are our vertical asymptotes?
Negative 4 and 0.
Uh-huh. Okay. And so x equal negative 4, x equals 0. How about horizontal asymptotes?
One.
Actually not. In order to figure out the horizontal asymptote, I need to figure out what the highest degree polynomial is going to be in the bottom, and it's going to be x squared, right?
Oh, so it doesn't mean it does not exist.
No, it means it's at 0. Whenever the highest degree in the denominator is bigger than the degree in the numerator, automatically y equals 0 is a horizontal asymptote. Okay, so now we have a layout where we have two vertical asymptotes and a horizontal asymptote. Well, these typically are going to look something like this, and maybe this, and then in between the asymptotes it can go up like that, or it can turn around and come back down. So we need to answer questions such as end behavior and intercepts. So what is our y-intercept?
3 over 4.
There is no y-intercept?
I said 3 over 4.
No, I know. But what I'm saying is there is no y-intercept. Why? Because the y-axis is a vertical asymptote. And vertical asymptotes can never be crossed by the function. There's no way I'm ever allowed to cross that asymptote or that asymptote. Because the moment the function has this value on the x-axis, then we're dividing by 0. So there are no y-intercepts. How about x-intercepts? In other words, if I set that equal to 0, can I solve that equation? Well, yeah, if x is minus 3, right?
Mm-hmm.
So at minus 3, there is an intercept. Okay, that's helpful. That means we're going to go through the x-axis. So most likely it's going to look like this. In the middle there, in between those two asymptotes. Let's make sure that we're in that quadrant right there. How would we do that?
You would plug in the number.
Okay, pick a number for x that's to the right of that asymptote.
-2.
No? Let's, over here. In other words, this is the 0 right here.
Or 1.
Okay, so if we plug in 1, we get 4 over 5, a positive number. Okay, positive number means we're in this quadrant, not this quadrant. Okay, now, typically when you come in, if you start from the right and you're looking at asymptotes and it's going up to infinity there, then it's going to start from down here, negative infinity, immediately to the left of that asymptote. And let's just pick a number, -1, and test that. Well, -1 would give you 2 in the numerator and 3 in the denominator. That's definitely negative, 2/3. So right here, I'm in negative territory. So it looks like this is going to be a good model. And then let's check a number to the left of -3 and not quite the -4 to make sure this thing keeps going. I'm sure it will. So if we check -3.5, let's make sure that result is positive. Well, that gives you -0.5 in the numerator, -3.5 times a positive half. That's a positive number. In other words, that whole thing is positive, which means this thing does this. And then again, since I'm approaching this asymptote and headed towards positive infinity, it's going to come out down here. Kind of think of it as if you went in a straight line towards the edge of the universe, eventually you'd come back on yourself. In other words, if it goes out at positive infinity, it comes out on the other side of the asymptote from the opposite side, negative infinity. And x-intercepts at -3 only. Does that answer everything we need on that? Here, I'll tell you what, let's graph these on Wolfram Alpha just so we can get confirmation here. X plus 3 over a quantity x plus 3 divided by the quantity x times x, what's the rest of it, plus 4. X plus 3 over x times x plus 4. Wolfram Alpha always gives you a couple of zooms. In other words, this is the one we're kind of looking at here. Notice, and then this is a close-in zoom, so you don't see this part in this picture here. But notice that's the way I've drawn it. We have a negative asymptote at about -3. We have a vertical asymptote at about -3, and we have a vertical asymptote at 0, and it does exactly what I thought it did. Okay. What else?
X over x squared plus 4.
Vertical asymptotes.
2, -2.
Is there anything that makes the denominator 0?
2 and -2?
No, it doesn't. 2 squared is 4 plus 4. -2 squared is 4 plus 4. So there is no value that will make the denominator 0. There are no vertical asymptotes. Is there a horizontal asymptote?
No.
Actually, there is. it's y equals 0. Notice why. It's because the degree of this polynomial is 1, the degree of this polynomial is greater. It's 2. Whenever that is the case, you have a horizontal asymptote at y equals 0. Let's talk about intercepts. Is there any y-intercept?
No. It is 0.
0. Is there any x-intercept?
0.
Okay. And again, this should be hyperbolic in nature, but there's no vertical asymptote. So let's see. What was that going to look like? Let's see. If I pick any positive x, then I have a positive result. If I pick any negative x, I have a positive result. So I'm in this area of the graph. No matter what I pick for x. This is strange. I don't have any idea what this is going to look like. Let's try some numbers and see if we can get a few points on here. We know it goes through here. And that's interesting because it goes through the horizontal asymptote. And that's allowable. You cannot go through vertical asymptotes, but you can have the function go through the horizontal asymptote and go through oblique asymptotes. The technical definition of a horizontal asymptote, it's what the function approaches as x goes to infinity. And it's going to approach 0. Okay? So, let's see. If I let x equal 1, let's put a grid on here. 1, 2, 3. When x is 1, y is going to be about a fifth. When x is 2, y is going to be a fourth. When x is 3, y is 3/13, which is slightly less than a fourth. And as x gets really big, for instance 10, then it would be 10 over 104, or like a tenth. So we can kind of see what this thing is doing here. As x gets big, it's going to approach that horizontal asymptote as x goes to positive infinity. And then on the other side, it does exactly the same thing. It's a reflection of this, because this function is odd. It's even, rather. No, no, it's not even. It's, I was wrong. We're not in this area. In other words, when x is negative, y is negative automatically. So we're automatically in this area, which means it's going to do what? It's going to do the exact reflection of this and come back and approach the y-axis like that. So I believe that's what this function looks like. Yeah, because when x is minus 10, then we have minus 10 over 104. So this function looks odd, doesn't it? It appears to have symmetry with the origin. Well, if an odd function is defined as this, it is odd, because when I plug in minus x, I get the negative of that, which is just putting a negative sign in front. So it does fit the definition of odd, and it should be symmetrical with the origin. and it appears to be. And there's only one intercept, right there. It approaches the horizontal asymptote as you go towards negative infinity, and it approaches the horizontal asymptote as you go towards positive infinity. Now, an interesting question here would be, where's the peak? Where's the upper bound here? They didn't ask that on this, did they?
No.
I think we would need calculus to calculate that. Yeah, I'd have to take the derivative of that, set that equal to 0 to know where that point is coming from. Okay? It's essentially the way we're going to want to do all of these is figuring out the asymptotes, x-intercepts, and the in-behavior, all of those good things. What else you got?
4x over x minus 2.
4x over x minus 2?
Yeah.
Okay, vertical asymptote?
2.
X equal 2, because that is the equation of a line. It's not a point. Horizontal asymptote.
4.
Yeah, y equal 4. Y-intercept.
Negative 2.
If we plug in 0 for x, we get 0. So there's the y-intercept, and obviously when the y-intercept is 0, well then that's also the x-intercept. We can see that it's both a y and an x-intercept right there. Okay, plug in a number to the right of 2, and let's see where we're at here. Let's see, that's at 4. In other words, again, this is going to be hyperbolic. It's going to look like a hyperbola. We just need to know which quadrants to put it in. So, if I plug in 3, what is f of x?
12 over 1.
Okay, so 3 would be about here. So whenever x is 3, f of x is 12, that's the quadrant we're in. And it's going to look something like that. And that means also that it's going to look like this in the opposite quadrant. And I think that sums up that function totally. Let's just check. Well, yeah, actually we checked it, because if we put in 0, we're in 0, so we know we're in this quadrant down here on the left. Okay? Got more?
2x over x squared minus 4.
Vertical asymptotes.
2 and negative 2.
Yeah, x equal 2 and x equal negative 2, which gives us one of these pictures where we have the double vertical asymptote, and then we always have, what's the horizontal asymptote?
No, 0.
0. Y equals 0. Okay. x-intercept and y-intercept is 0 again. Which quadrant? Are we in this quadrant here? And how can we find out?
Quadrant 3.
Okay, what does 3 give us? Gives us 6 in the numerator over 5 in the denominator, positive 1 and a fifth, so we're definitely in that quadrant. That tells us that it looks like this, and almost certainly looks like that, and looks like this. Let me just check this one on the left. If I plug in -3, then I get -6 over 5. That's an accurate picture. There's nothing else they wanted? Did they ask about end behavior on any of these?
No.
But you kind of have to know it in order to graph it. Because you're expected to graph these manually, right, without your calculator?
Yeah.
Okay, that's what I thought, yeah. Yeah, and it's really kind of as straightforward as that. Now, a lot of times, these kind of graphs won't cross the x-axis. They'll do something like this, turn back around and come down, and then it changes the location of that. In other words, that ends up being there like that. And that's a very typical looking graph. And we would be able to tell whether it had this appearance if there were no x-intercept. Then we'd know that we're going to be looking at something like this. In other words, if it doesn't go through the x-axis, what else can it do? It's got to turn around and come back down, assuming we had a y-intercept like that. But this is a pretty typical hyperbolic graph also. But not in this case, because we did have a y-intercept and this crossed through the x-axis, then on this side, it's got to be down here. I believe it always has to follow that rule, that if it goes to one side of the vertical asymptote on negative infinity, it's got to start on the other side at positive infinity and vice versa. I don't ever remember seeing... Well, hold on. I may have an example that contradicts that very statement. What does this look like? 1 over x squared. It has a horizontal asymptote there, a vertical asymptote there. It goes like this and like this. So that statement I made isn't true. In other words, obviously, we approach this vertical asymptote at positive infinity, and we come back on the other side at positive infinity. All right, what else you got?
X squared plus x minus 12 over x squared minus 4.
Minus 4?
Yeah.
Okay. It's always a good idea to factor, if you can, top and bottom. And the reason being is there might be something that cancels out. There isn't on this, but there could have been. And if it cancels out, you need to cancel it out, leaving a hole instead of a vertical asymptote. What does the top factor into?
X plus 4, x minus 3.
Huh? And the bottom?
X plus 2, x minus 2.
Uh-huh. So nothing cancels there, but we can go to our vertical and horizontal asymptotes. Vertical?
2, -2.
Horizontal?
1.
Where are we at over here? Now, hold on. Let's do intercepts. What is the y-intercept?
3.
Let's see. If I substitute x for 0, what do I get? Minus 12 over minus 4. You're way ahead of me. So positive 3, which is above this horizontal asymptote. So there's our y-intercept. Do we have any x-intercepts?
Would it be negative? No, would it be false?
It would be wherever the numerator is negative. Excuse me, it's wherever the numerator is 0. In other words, if I set this whole thing equal to 0, which is what you want to do to figure out your x-intercepts, because that's where y is equal to 0, and I go to solve this, well, it can only be equal to 0 if the numerator is equal to 0. And the numerator is equal to 0 when x is minus 4 or plus 3. So over here at minus 4, or right here at plus 3, we have 2 intercepts on the x-axis, one there and one there. Okay, that tells me that we're going to be down here, right? In other words, well, we better still find out. Let's plug in a number. To the right of 3.
4.
Yeah, let's try 4. What does 4 give us? It gives us 8 times 1 divided by 6 times 2. That is below that horizontal asymptote. That's 8/12. So this picture does fit this set of asymptotes. Okay? Now, what's going on in the middle? The fact that we go through this x-intercept over here means that that's that picture. And the middle maybe does this. Let's see, because there are no x-intercepts, hold on a minute. Let me think about that picture. Pretty sure that's the way the picture is going to end up being. Let's figure out if it crosses the horizontal asymptote. Because my picture down below that horizontal asymptote might actually be wrong. In other words, it's theoretically possible for one of these things to do this, which is to come up, cross the horizontal asymptote, and then come back and approach it. So in order to figure that out, whether it does that or not, we need to figure out if this function ever crosses the horizontal asymptote, which is y equal 1. Well, in order to do that, let's solve it and see if this has a solution. If I set y equal to 1, can I solve this equation? Well, that would mean that that has to equal that. That's when y would be equal to 1. Well, let's see if that has a solution. I'm running out of room, but I'll work right here. So does x plus 4 times x minus 3 equal x plus 2 times x minus 2? if this has a solution, then we do cross this horizontal asymptote. Well, I guess I need to put it back together in order to solve that, because it boils down to x plus that equals x squared minus 4. Well, I can cross out the x squareds, and I got x minus 12 equals minus 4, so x equals 8. When x equals 8, it is crossing the asymptote somewhere over here. There is a point on that graph right there. Did you see how I got that?
Yeah.
Okay. And that means that, and that was the only solution I came up with, so it means that what we do here is we cross the horizontal asymptote, and then we end up approaching it from above. Whoops, excuse me. Hold on, I drew that picture wrong. We got to go through this point right here. And we have to stay. The question is, am I below that or above it? When x is 10, what do we have? We have 14 times 7 all over 12 times 8. Is that number greater than 1? 98. No, it isn't. Yes, it is. 98 over 96. So to the right of 8, we are above that horizontal asymptote. So my picture is correct. But notice everything I had to do to discover it. To the left over here, I'm below the horizontal asymptote the whole way, because I didn't have any points in negative x territory that crossed the horizontal asymptote. So we still haven't figured out what's going on in the middle yet, other than we're right there and we do not cross this horizontal asymptote, so it almost has to do that. Let's graph this function on Wolfram alpha and have a look at it. Quantity x squared plus x minus 12 divided by x squared minus 4. Is that what I was supposed to have? X squared plus x minus 12, x squared minus 4. Okay. Okay, I got it right there. So this is a little hard to see because they don't show you one picture that has all of the important points in it. But notice the close-up. Got an asymptote at 2 and negative 2. And I drew that correctly. Notice that if I put the line on 1 for the horizontal asymptote, I cross it at 8, and then I spend the rest of the x-axis approaching it, getting closer and closer to it. And in the middle, it does exactly what we thought, crosses the y-axis at 3, goes back up to infinity, and on the left, to the left of minus 2, we get a glimpse of that little piece right there, which turns into that. So it does do exactly what I drew. That was a tougher one. That's the first one we've seen that crosses the horizontal asymptote. We really probably should have checked all the others to see whether it does. And you can always test to see whether it does by setting the f of x equal to that horizontal asymptote and seeing if you get a solution. And we did. All right. What else?
X squared plus 6x plus 8 over x squared minus 4.
Okay, this one's going to factor a little better into what? I know you know that one.
X plus 2, x minus 2, x plus 2.
Okay. Vertical asymptotes.
2 or negative 2?
No, this is a case where this factor crosses out that factor. So it leaves me with only a vertical asymptote at 2 and a whole at minus 2. And that's kind of the way to write that. That's a whole. Horizontal asymptotes.
1.
So there's one vertical asymptote and one horizontal asymptote. X-intercepts. Or Y. We'll do it in the same order we've been doing it. Y-intercept.
Negative 2?
Yeah. Which is right here. Let's see. If that's 2, then so we have a Y-intercept there. And X-intercepts? It's a little tricky. What makes the numerator 0?
Negative 4?
That's it. That's the only one. So, and I'll explain why in a moment. So we have an x-intercept there. We don't have one at minus 2 because we've already stated that x can never be equal to minus 2. So there's going to be a hole at minus 2 in this graph, and we'll draw it in there after we graph it. But the only x-intercept is minus 4. And now, let's determine whether or not it crosses that horizontal asymptote. And how do I do that?
You set it equal to 1.
Yeah, and so I want that to be equal to 1, basically. Well, is it? X plus 4 equals x minus 2. Does that have a solution? No, the way you can tell is if you cross out the x's, which you can certainly subtract x from both sides, you're left with one number equaling another number. That says there's no solution to that little equation right there. That tells us that this graph never crosses this horizontal asymptote. Otherwise, that would have a solution. Okay? Behavior to the right of 2. Where does it put us?
Positive.
But how big a positive? Because we need to know whether we're above or below this horizontal asymptote. So if we plug in 3, we get 7 over 1. So we're in that quadrant there. Okay, and there's not much left to do. We've got everything we need. We know it's approaching the vertical and the horizontal asymptote in that quadrant. And the other side has to do the same thing. I know it goes through there, and I know it goes through there. In other words, all of our x-intercepts, y-intercepts. Oh, and the last thing to add here is the whole. Well, that's minus 2 right there. And so if you're doing it manually, you can add that whole like that. Would that show up if I put this in Wolfram Alpha? Or would it show up in your calculator? If you were to input that into your calculator, would you see that whole?
I'm not sure.
You would not. And the reason is that it is infinitesimally small. You can draw it in to indicate its presence at minus 2, but when the graph goes to graph it, it has data points. Remember, there are an infinite number of points between minus 1 and minus 3. And minus 2 is just one of those infinite number of points. So it's not going to have any thickness that you could see. And that's the only way the computer does it. Now, I suppose that there could be computer graphic programs that would know of the existence of the whole and put one in. But Wolfram Alpha doesn't do it, and my TI-84 didn't do it. So I've never seen a computer put the whole in. But it's definitely there. In other words, just because I factored out x plus 2 from the numerator and the denominator does not take away my domain restriction, because this is the original function. And for sure, x cannot be minus 2, otherwise I'm dividing by 0. And that is certainly something you cannot do in math, is divide by 0 ever. Okay? You're getting progressively harder. What do you got up next?
X plus 7 over x squared minus 49.
Vertical asymptotes.
7.
Holes.
Negative 7.
I guess you write that like that. That's kind of an odd way to write it, isn't it?
Yeah.
But you can't really say there's a hole at x equal minus 7. Maybe you can. I'm not sure I need that there, but I kind of think I do need that there. Do you know?
Wait, we didn't write it? No.
You don't put the line across the equal sign? Okay. So you just have the hole as x equal minus 7?
Yeah.
All right. That makes sense when you think about it. That's exactly where it's at. So, okay, horizontal asymptotes.
1.
Y-intercept.
Negative 1 over 7?
Correct. Negative 1/7. X-intercepts.
I said 0. Wait, no, negative 7.
Negative 7, correct. Okay. And does it ever cross the, let's see if we can solve for whether it crosses the horizontal asymptote or not. And I'll try to do that before I draw the graph so I have room. In other words, can I solve this solution? X plus 7 over x minus 7 times x plus 7. Is that ever equal to 1?
No.
About when x is equal to 7. Ah, x can't be equal to 7. In other words, Oh, yes. No. So the function is 1 over x minus 7, which would be equal to 1 when x is equal to 7, but it can't be equal to 1 because it can't be 7. So no, it does not cross the horizontal asymptotes. So we're ready to graph. Vertical asymptote at x equals 7. Horizontal asymptote at y equal 1. Y-intercept right there. X-intercept at minus 7. About right here. Ooh, boy, they did get progressively harder. Because that's where that hole is also. So there's no x-intercept. It's going to go through there, but there's going to be a hole there. Okay, so we're certainly on this end over here. And in fact, I can draw it. Which means we're up here also. And now, instead of going through the x-axis, I'll draw the hole at minus 7. And that fits everything. Doesn't cross the horizontal asymptote, crosses the y-axis in the right spot, crosses the x-axis, but it never is on the x-axis because of that hole. Okay? Got probably time for one more at least.
X over x to the fourth.
X over x to the fourth?
X plus 4.
Excuse me. X over x plus 4. This looks familiar. I think we did this one as the very first one.
Oh, yes, we did. Okay. Well, these are all repeats.
Okay.
X squared minus 4 over 2x?
X squared minus 4 over 2x?
Yeah.
Okay. This has got a very unusual thing that we haven't encountered yet. What is that? The numerator has a higher degree than the denominator. So, what we have to do here is do the division. And to do the division, we need to put in that dummy variable. Do you know how to do this kind of division? What goes here?
1?
1/2 x. Remember that whatever goes here has to multiply that to produce that. In other words, now I multiply it back and I get x squared. I subtract, that's 0. That's 0. Bring down the 4, that's my remainder. Minus 4 over 2x. So, when you have this situation, you have an oblique asymptote. In other words, if the degree in the numerator... What's that?
We never got to that.
Okay, well, I don't know if you will in the next day or two or not, but since we only have 5 minutes, let's talk about it anyway. There is a vertical asymptote at x equals 0. We obviously can't divide by 0. There's no horizontal asymptote, but there's an oblique asymptote. Whatever you get as the quotient, when you do that division, that's the equation of your oblique asymptote. Has a slope of 1/2, goes through the origin. So there's my grid that I'm dealing with now on this function. And oblique asymptotes mean that the function approaches that oblique asymptote as x goes to infinity. Now, the question is, how do I graph this thing? Typically, these look something like this. That's assuming it is allowed to cross the oblique asymptote, but that's not something that's easy to figure out. And there's a lot of things about these kind of graphs that are hard to figure out. For instance, where is the range bottom? There, and where's the range top? There. So these kind of functions, you kind of need a calculator to graph them. I mean, you can figure out that I'm in this quadrant. Let's just check to make sure I am in this quadrant here. If I use a value of 1 for x, I'm in the wrong quadrant I picked. It's not there, it's here. And here. Because when I plugged in 1 for x, I got -3/2, which is about there. Y-intercepts. We have a y-intercept?
No.
No, because it would be, in other words, I can't plug in 0 for x. That's the vertical asymptote, is x equals 0. So vertical asymptote, x equals 0. You have the oblique asymptote, which is y equal 1/2 x is the equation of that line. You don't have a horizontal asymptote. Actually, you might. No, you don't have a horizontal asymptote. I don't think you ever have a horizontal asymptote when you have an oblique asymptote. Even though this is equal to 1/2 x with a remainder of 4 divided by 2x, in other words, if I looked at that part of the function, that's hyperbolic also, and you can't ignore that. That's the answer when you divide x squared minus 4 by 2x. Let's see. So there's no y-intercept. Is there an x-intercept? Looks like there is. Looks like there's an x-intercept right there and right here. What would those 2 points be? Remember, the x-intercepts are where y is 0. So can you solve? If I set that equal to 0 and solve. Remember, it's only equal to 0 if the numerator is equal to 0. So those 2 points come at plus or minus 2. And now the picture of this is rapidly taking form. And this is what it looks like. All right. Any other questions, Nina?
So let's say you have x squared minus x minus 6 over x plus 2. and then it ends up being x minus 3 over 1. Would the vertical asymptote just be 0?
Give that to me again.
So you have x squared minus x minus 6 over x plus 2.
Okay, so this would be x minus 3 times x plus 2 over x plus 2. These cancel, and you're left with a whole at x equal minus 2. And the function ends up graphing as a linear function, just like that. Only there's a hole. There's a hole right there.
Oh, okay.
In other words, it graphs as x minus 3, with the exception of having that hole. Mina, unfortunately, I have an 8 o'clock that I have to get to, so I'm going to have to let you go.
Okay.
Okay? I will speak with you next Wednesday night.
All right, thank you.
You're welcome. Bye-bye.